Well, shalom. I hope you're doing well. This video is the first of a multi-part series on CFD for aerodynamics and Formula SAE. This series assumes no experience in computer-aided design or computational fluid dynamics. The scope of this series is to get the user introduced with a very simple project to get experience with the fundamentals of CAD and transfer the said model to be run in CFD. And so before we get started, if you want to skip right to the CAD, I'll post a timestamp in the video description below. So first things first, why are we doing this? Well, designing an effective aero package requires testing and validating the capabilities of said package to analyze the effects it has on the incoming airflow and look for possible improvements based on your design requirements/goals. Currently, there are three ways to test an aero package. There's road testing, there's wind tunnel testing, and computational simulations. So road testing really seems to be the most attractive of them all. I mean, it makes sense. Like, if you're designing for the road, then test on the road. However, there's quite a lot of caveats when it comes to road testing. Uh, for instance, the moment we think about measuring distinct characteristics such as lift, drag, pressure, distributions, and etc., we find that it's very hard to do so because of a lot of variables that are just simply not in our control, such as suspension vibrations, varying ambient conditions, the list goes on. And it's also incredibly expensive to manufacture all those parts just to be tested on and not be the final project. And so, on the topic of having variables in our control, wind tunnel testing is phenomenal when it comes to accurately testing the aerodynamic capabilities of a physical package. However, there's still drawbacks to this method. Um, Full-scale models are expensive to manufacture and may not even be available or built yet. Um, Therefore, making smaller models preferred, but they do not replicate the full-scale effects exactly to a T. Uh, Not to mention the walls and the stationary floor produces problems that are just simply not realistic like a racetrack. And finally, we have computational simulations. And this method has the ultimate control when it comes to testing. It seems to answer all the problems faced by wind tunnels. Um, However, we're still limited because running CFD is incredibly time consuming. Using fully detailed models require a ton of resources, and even that is near impossible to replicate in CAD, which is why it is a common practice to create simplified models. Uh, the CFD testing is often the first go-to method when designing an aero package. The reason why we want to run simplified models is due to the same reason why we can run smaller models in wind tunnels. Although the results may not be the same as the full-scale model, uh, the results will still mimic and be very similar to that of the full scale. Now, for validation, though, you would still need to test these multiple methods to see if, in fact, your package is producing the results you want. So, ideally, if you can validate your package using all three methods, then you have either cracked the system or have used witchcraft. So, with that being said, there are a couple practices we need to keep note of before having at it with CAD. So units, for an example. Although it may be self-explanatory, units must be consistent. If you're reading measurements in metric, then CAD in metric, or at the very least, convert the units and then CAD with that. Uh, and then we have coordinates and placements. Now, coordinates are very important because they're the standard when it comes to CFD. X is forward, Z is up, and Y is out the driver door. It is also very important that you keep in mind where you have your origin. Usually you want to design your model with the origin being right below the center of your front wheels, touching the ground, accounting for the squish of the contact patch. Or if you're modeling airfoils or bare wings or just models without wheels, then design a model with the origin at the very front of the model. And so the program we will be using for CAD is SolidWorks. SolidWorks is a computer-aided design and engineering program that is centered around sketch-based modeling, meaning most of the models start off with a 2D sketch. Uh, you can create uh, models called parts and then put those parts in a larger assembly, which is a conglomerate of the multiple parts that you made, um, creating an entire system. Uh, so think of a 4-bar mechanism. The whole system would be an assembly file, um, while the individual bars will have their own separate part files. Uh, SolidWorks also has a feature where you can document the dimensions of specific parts and save them as drawing files. Uh, this is more of an aspect for component engineering, which we don't have to worry about right now since we're just worried about making CFD oriented models. Um, and speaking of the model in question that we are going to make is a very common one called the Ahmed body, which in short is the benchmark, well, a benchmark model widely used in the automotive industry for validating simulation tools. And so without further ado, let's get started with SolidWorks. Um, However, before we do, a very optional but equally encouraged practice, some would say step 0, is you gotta find a vibe. So as many engineers in your school or in the industry will tell you, you'll be spending a lot of time 3D modeling complex parts and assemblies. So it is very encouraged to keep your mental health at bay with some music of your choice. And the symphony that I will be selecting is going to be a dear old classic of mine from my childhood, from Sly Cooper 2, Band of Thieves, as I think this will be um, very fitting as we set up our plan of action. So first we got to look up the model. So let's look up Wake Refinement, Betcher Devo, and select the first one by ASME. Then click on the PDF. And then once you have the model here, I like to take a snipping tool. And then we can analyze this. Okay, so already noting, like, we have our model that is in um, millimeters right here. So right now we have no wheels, right? So that means we want to have our origin right in front of the model, and connecting with the ground plane. So let's label the red as a ground plane. So our origin is going to be over here. So we can also do a little bit of trickery too, because we see that the right height is also at this specified distance, so 55 millimeters. And of course our coordinates, you know, x is forward, and then z is upwards, and then coming towards us is going to be y. So now that we can, well, so now we have like a plan of action. Let's go ahead and just shift this to the side, and let's open up SolidWorks. I'm out of water. Dang it. Yeah, it's okay. I get it. Oh man. Okay, so right here, we want to make a new part. Okay, so then when you first open up SolidWorks, you'll be greeted with just a blank screen, and that's totally fine. Let me just move this tab over here. That way we don't lose sight of our model. Excellent. Okay, so over here on the left, we have our design tree, and this pretty much keeps it keeps a history of every little change you do in your model. So let's go ahead. Oh yes, and also over here we have the origin. So remember, right, x is forward, z is up, and y is out the door. So we can reorient ourselves using, well, holding like the middle mouse button and just like having it like this. Or we can press the space bar and then reorient ourselves in a way that we can no, not that. Come on. Close. Okay, this is about as good as we're gonna get. Alright. So we have our ground plane, and that's gonna be labeled the front plane. We can rename this. So just click on it, and then we're gonna label this as ground plane. Excellent. And so we want to make our right height plane now. So we're going to go into, I believe it is features, and then reference geometries, and then we click on plane. So it already selected like the ground plane as a reference, so that's pretty good. And so we want this to go up 55 millimeters. So we can easily just 55 millimeters like that, and we're set. So this will be, well, let me rename it. All right, right height. Excellent. Okay. So looking at our model, it's pretty. We can set this up as a two-piece. So Everything above the right height plane we can simply just make with a single block, and then on the bottom we're gonna have four cylinders essentially. So let's get started on the top block right here. So let's just go ahead and create a sketch, right? On the sketch mark, and then you want to select a rectangular tool and literally just make a generic rectangle. Like, it really doesn't matter what you do with this, because the real magic comes from our smart dimension and also these. So let's go ahead and click on one of the sides, and we see that we have a length of 1044 millimeters. So 1044 millimeters, just like that. And we have a total width of 389 millimeters. Excellent. Okay. And we can essentially extrude our block now because we have a sketch, right? But let's say, well, if you hit escape, you can exit out of smart. Yeah, right here. So let's say we didn't place our plane on the origin, right? So we're over here. We can then use smart dimensioning again to mark the origin, and we can zero our values. So just like add a 0, and same with over here. We want to dimension one. Give me a second. No, I don't care about this line properties. Here we are. So we then dimension with respect to the origin again. If I can click on it. No, that's totally fine because I can probably just click on the origin from here. Yeah, here we go. Okay. And then to make sure that this is even, we know that it's 389, so if we just do 389 divided by 2, because it can do math like this on the go, and boom, we're now centered. And now we have our sketch fully defined, and now all we need to do, just extrude. We have to here we go. Alright. So we can so the height of this block is essentially 288 millimeters. Just like that. We can also, if you want, extrude in the other direction. We can even make this a thin feature too, so like a cavity. But we're only interested in our block. Alright, so once we have that, we now have to make these features. So for these front features, it's going to be a fillet, and so if you go to the Features tab and then click on Fillet, we can then select, oh, hang on, it's this side, yeah. There we go. We can select each of the edges we want to fillet, and then specify that we want this as 100 millimeters. And Shazam. Alright, so now we have to worry about the tail. So it's going to be a chamfer of 25 degrees. So chamfer, I believe, is right under fillet. Yes, it is. And we're not going to want to do this. Okay, so we have the angle, but it also needs a distance, which we already know is this distance right here. And we can see that it is just a simple subtraction of 1044 minus 843 millimeters. And we can flip the direction. And we're golden here. So as it stands, we have the first part done. Now we just gotta worry about its stubby little legs. So these legs, these legs don't seem to be mentioned with their diameter, so we're just gonna eyeball it. That's what you don't want to do, like in real life, though, to be honest. You never want to eyeball something. Except maybe pizza, that's pretty good. Alright. So now we're going to create small holes, pegs, whichever, really. Doesn't matter where, right? Because our smart dimension tool is going to take care of that for us. So we're going to have, yeah, about 0.05, so let's just put that 0.05 meters. 0.05 meters. 0.05 meters. And same thing over here. Okay. So aligning these guys is going to be very important. And so to do that, right, we want to click down and we want to, so let's say, so let me take a step back for a moment. So I want to be able to move this circle and have all the other circles move along with it. So in order for me to do that, I once again have to use a smart dimension tool. So if I want to constrain this circle with this one and vice versa, I just have to zero those distances horizontally, and same with these. Excellent. So now if I move, so now if I move this circle, which it won't let me do, alright, if I move this circle, it'll move along with it, but not vertically. So once again, I have to constrain them vertically, which I have that I mentioned over here. So we got 296. So let's do vertical dimensions. We have 296 millimeters. And then 296 millimeters. All right. All right. So if I'm, oh my God, stop, please. Okay. So if I move this circle, it moves along completely fine. But now it's disconnected from our rear legs. So let's go ahead and do the same thing. So we have a wheelbase of 525 millimeters, and track. Oh, yes, that's right. I then need to 0 vertically. Excellent. So now it should be, yeah, here we go. Okay, so if I move this circle, it moves along all in one motion. That's good, that's what we want. And so my mentioning is very important because it gives you a detailed constraint of what your model should look like without any obscurities in your design. It's also very useful in the long run if you plan on running multiple iterations of one model. Let me digress for a second, such as this wing element configuration that I have done a while back. So let me open up the sketch, edit. So dimensions are very powerful if you know how to plan with it. So instead of starting a sketch from scratch, so instead of having a part start from scratch each time, if you play with the right, well, if you dimension your base part just right, you can then just manipulate those and then save yourself a lot of time. So for instance, if I wanted to change the clearance of the main elements, so I'll say 5, right? Then, oh, that's not supposed to happen. So let me dimension this vertically with the origin. Okay, so retry. So if I want to change the clearance height on this, I can do so, and all the preceding elements will change along with it. And I can change the trailing and leading edges by just a few clicks, right? And if I want to change the angle of attack on the rear, so make it more aggressive, I can make changes on the fly without having to start from scratch. So really, dimensioning is an incredibly powerful tool that you can utilize if you can do it correctly. Alright, so back to our model. Let me then, come on, stop it, stop it, please. Let me just move you. Okay, here we go. Alright. So, and now we have to center our stubby legs. So I know that it is 200 millimeters from the front of our car so 200 millimeters, just like that. And it is also, apart from the origin, it's going to be half of a 296. So let's go into vertical. And click on the origin. Well, try to. There we go. Then we're going to go 296 divided by 2 millimeters. And boom. Excellent. And now with our sketch completely mentioned, we can then finally extrude all four at one time. So I don't want it to extrude this way, so let me just extrude the opposite way by just switching like a binds. And so if I want to make a perfect fit to our ground plane, I can select up to surface and then select the ground plane as that surface, and now our model is complete. So, but let's say you messed up, like at the beginning, and you had your origins at not X is forward, Y is up, and sorry, Z is up and Y is out the door. Well, you don't want to restart the entire part. No, there's a pretty sneaky way that you can do it. So let me just show you. So first we have to make a point, and we'll put this point at the origin. So now we can place our coordinate system, well, a new coordinate system at that specified point. So now we have the x-axis going this way, and yeah, let's say for some reason we want this as our coordinate system. So when we save the part, we can then save this part and save it with its new coordinate system under pair solids. Now, so STAR-CCM does take step files and STL files. I'm more used to pair solids because that's just what I learned from the video. And under the options, right here, the output coordinate system, you can save yourself a lot of time by just going with the new coordinate system. But we don't want to, right? Because we did it right the first time. So now let's just label this over here, and now we have our Ahmed body. And that's it. That concludes the rest of this video. I'll see you guys in the next video, which I will cover STAR-CCM and geometry prepping and meshing. Other than that, I hope you guys have a splendid day, and I'll see you next time.